Imagine this. The ground is rushing up. You see this massive aircraft, maybe a Boeing 737, coming down fast.
Mm-hmm.
But here's the thing. The pilots, they're not really leaning on all those super high-tech automated guidance systems you'd expect.
Right.
They're bringing this huge jet down, like almost entirely by sight. It's this incredible mix of pure skill and just reading the cues, a real high-wire act up there.
It really is.
So how on earth do they do that? Today, we're doing a deep dive into something pilots call the visual circuit.
Yep.
It's this really fascinating, highly skilled maneuver. It lets them land these big planes, even jets like the 737 when they don't have that fancy instrument guidance, you know?
Exactly. And our guide for this is the Commercial Pilot's Handbook by Captain Ashutosh Chopra. We're digging into his Chapter-10, which is just called a visual circuit.
Okay.
Now, he talks specifically about the B-737 parameters-wise, but the basic ideas. They apply to most big transport aircraft, what they call Type A.
Gotcha. So our mission today is to sort of pull back the curtain on how this manual flying skill actually works.
Mm-hmm. We want to unpack the subtle factors, these specific approach gates cues, really, that pilots use.
Right, these markers.
Yeah, and how even when flying visually, there's this surprising kind of clever mix of just sharp observation and also using technology smartly to nail the landing.
It's a cool blend.
So get ready. You're going to see the world from the cockpit, but kind of without all the usual overwhelming data streams.
Okay, let's set the stage. What is a visual circuit exactly? And it's really important to stress it's not the same as just a visual approach.
Oh, okay. What's the key difference then?
The absolute key is that a visual circuit requires visual meteorological conditions. VMC. That's mandatory.
VMC. And that's not just like a nice sunny day. It's more specific.
Yeah, much more specific. Generally, you need pretty good visibility, think around 5 kilometers usually.
Okay.
Plus, you need specific distances from clouds, typically 1,500 meters horizontally and 1,000 feet vertically.
And the big one.
Yeah.
The pilot absolutely must have the runway and the terrain in sight at all times. No exceptions.
Wow. Okay. And this can be day or night.
Yep, day or night. The specific VMC rules can change a bit depending on the country, the type of airspace, altitude.
Yeah.
But down low, near an airport's control zone, those are the typical figures.
So what makes this particular maneuver stand out so much?
Well, think about standard instrument approaches. They've got radar control helping out, detailed charts showing every twist and turn.
Right, lots of support.
Exactly. But a visual circuit, it's a very manual skill, and honestly, pilots don't practice it nearly as often.
Really?
Yeah. So it puts the entire responsibility for managing the descent path, controlling the speed, getting the flaps gear out at the right time.
Yeah.
It's all directly on the pilot.
Wow.
It's pure stick and rudder skill, basically, combined with some serious mental gymnastics.
That sounds incredibly demanding. I mean, the mental workload?
Oh, absolutely. Pilots need this really solid mental map. They have to visualize their approach direction where the runway is oriented, the whole circuit pattern.
As if they don't.
If they don't, they could easily mess up the entry, maybe even line up on the wrong runway or a taxiway, which you can imagine is a very bad situation.
Yeah, definitely want to avoid that. So, okay, how does a pilot actually start this? How do they join this circuit?
Captain Chopra recommends joining from what's called the dead side of the airfield.
The dead side.
Yeah, it usually means flying over the airfield first and then approaching the circuit from the side opposite to where the active landing traffic is.
Ah, okay. Why is that better?
Well, the clever thing about joining from the dead side is, first, it helps keep you clear of other planes.
Makes sense.
And second, it gives the pilot a really good look at the entire circuit pattern and any other aircraft that might already be in it. You get the big picture.
Better situational awareness right from the start.
Exactly. But at the very least, pilots should aim to join no later than the start of the downwind leg.
And the downwind leg is?
That's the part of the circuit where you're flying parallel to the runway, but in the opposite direction to your landing.
Got it. Okay.
And, one big plus of a visual circuit compared to maybe a straight-in instrument approach is the flexibility.
How so?
Because the pilot is constantly looking outside, jogging the flight path, checking the aircraft configuration. They have more freedom to adjust and join the pattern at different points, assuming it's safe. And they talk to ATC, of course.
Right. Coordination is key. What about talking to air traffic control?
Oh, yeah. That's essential. Pilots must tell ATC they're in VMC. They have to confirm they can see the ground, the runway, and crucially, any other planes around them.
Okay.
And sometimes, if there are other aircraft already on final approach, ATC might say, okay, hold your altitude for now.
So they can't just descend right into the circuit altitude?
Not immediately. They might have to stay a bit higher, maybe above the missed approach altitude, and then figure out how to lose that extra height smoothly once they're on the downwind leg.
Okay, this is where it gets interesting for me, that blend of old school visual flying and new tech.
Yeah.
You said even though it's visual, they use some advanced stuff.
Yes, exactly. It seems a bit counterintuitive, right? But pilots are actually encouraged to use the flight management computer, the FMC, and the map display.
Even on a visual circuit.
Absolutely.
Yeah.
They're not just for navigating across oceans. In this case, they become really powerful tools for boosting spatial orientation and just general awareness. It helps build that mental map.
How do they set that up?
Well, typically, a pilot would go into the FMC's fix page.
Okay.
And they'd punch in the precise location of the runway threshold, the very beginning of the runway.
Right.
Then they add these kind of virtual reference lines, radials, and distance circles, usually at common distances like 2.5, 5, and 10 nautical miles out from that threshold.
Being digital landmarks almost.
Exactly. And on another page, the descent page, they'd put in the runway's elevation. Sometimes in a funny format, like they might enter 70 if the runway's at 7,000 feet.
Okay.
But the point is, these digital references give them really valuable cross-checks for what they're seeing outside, even though they're fundamentally flying by hand and eye.
So let's talk about approaching the circuit. You mentioned those 10 and 5 mile circles they set up in the FMC. How do they use those?
Those become really crucial approach gates. Think of them as invisible checkpoints in the sky. They help the pilot manage the descent and get the aircraft configured correctly.
So like milestones?
Precisely. So around 10 nautical miles out from the runway, the target is generally to be about 3,000 feet above the ground AGL.
Okay.
And you want to be at what's called flaps up speed, basically. Clean wing configuration, no flaps extended yet, and already descending.
Descending towards the circuit altitude.
Exactly. Then, as you hit that 5 nautical mile circle, the aim is to be down at 1,500 feet AGL, that's usually the standard circuit altitude, and you're still at that flaps up speed.
Still relatively fast then.
Right. Now, between that 5 mile point and actually starting the downwind leg, that's when the pilot starts configuring the aircraft for landing.
Okay, what does that involve?
It means slowing down to flap 5 speed. So
Yeah.
they select flaps 5, which extends the flaps just a little bit.
For more lift at slower speeds.
Exactly. More lift and a bit more drag. And they need to be establishing themselves on the downwind track, often a specific magnetic track, like, say, 0-90 degrees if the runway is 270.
You mentioned track there, not just heading. Why is that distinction important?
Good point. Maintaining a specific track over the ground is key. You use the track line predictor on the navigation display, or the velocity vector symbol. Because just flying a heading doesn't account for wind. Wind can push you closer to or further away from the runway. Following a track ensures you maintain the correct lateral distance from the runway.
Got it. Wind correction is built in.
Exactly. And Captain Chopra actually suggests flying manually from this point onwards.
Taking the autopilot off.
Yeah, if conditions allow and everything's stable, it helps the pilot get a really good feel for the aircraft, how it's responding.
But only if things are under control.
Oh, absolutely. You don't want to be wrestling with the plane while trying to fly visually. And all this time, they're keeping an eye on the vertical bearing, the VB, and vertical speed, VS, on that FMC descent page we mentioned. It's another cross-check.
And visually,
Yeah.
What are they looking for outside?
Constantly keeping the runway in sight, of course, but also identifying key landmarks or features on the ground that line up with the runway's extended center line.
Why?
Well, if visibility gets a bit hazy, maybe due to slant-rained haze or sun glare, having those ground references helps maintain orientation towards the runway.
Smart. Backup visual cues.
Exactly. And this is also a really critical time to visually spot any other aircraft in the pattern and make sure you're maintaining safe spacing.
Okay, so you're established on downwind. What's next? The turn towards the runway.
Right, the sequence of turns. Downwind to base leg, and then base leg to final approach. This starts at a specific point on the downwind. Typically, it's when the aircraft is directly abeam, or alongside the runway threshold. On the map display, this often lines up with that 180-degree radial at 2.5 nautical miles they programmed earlier.
Okay, so they hit that point.
And the pilot flying starts a mental 40-second timer.
40 seconds. Okay, what happens during that time?
About halfway through, at 20 seconds, they take action. Lower the landing gear.
Gear down.
Select flap 15, extending the flaps further.
More flaps.
Adjust the engine thrust to maintain the correct speed for flap 15, and then retrim the aircraft, because extending flaps and gear changes how it wants to fly.
Lots happening in 20 seconds.
Yep. And by the end of that 40-second countdown, The aircraft should have slowed down nicely to that flap 15 speed. And there's another check. The vertical speed on the FMC should be showing a descent rate around 1375 to 1400 feet per minute. It's very precise.
Okay, 40 seconds are up. Now what?
Right at the 40-second mark, now the pilot starts the turn onto the base leg.
The first turn towards the runway.
Exactly. Using a bank angle of about 20 to 25 degrees, but they'll adjust that slightly depending on any crosswind.
And the other pilot, the one monitoring.
They're busy too.
Yeah.
They'll set the runway heading in the autopilot's heading selector bug as a reference, set the go-around altitude in case the landing needs to be aborted.
Safety backup.
And importantly, they turn off the flight directors.
Why turn those off? I thought they helped guide the plane.
They do, but this is a visual circuit. The pilot flying is making the judgments based on outside references and instrument cross-checks. Having the flight director command bars up can actually be distracting or contradictory.
Ah, okay. Pure visual guidance backed by instruments.
Precisely. And as soon as that turn on to base starts, the pilot flying reduces thrust just a touch, maybe 2-3%, and initiates a rate of descent, usually around 500 feet per minute.
Starting down towards the runway altitude.
Correct. Now, for the first part of this turn, maybe the first 90 degrees of it, the absolute focus is just on maintaining that bank angle, the rate of descent, and the airspeed, even if the runway view isn't perfectly clear at that moment.
That sounds tough. Turning accurately without necessarily having the runway perfectly in sight.
It is. And that's where another piece of tech helps. The map display's trend vector.
The trend vector, what's that?
It's a little line on the map display that predicts where the aircraft will be in, say, 30 seconds, based on the current bank and speed.
Ah, like a little flight path predictor.
Exactly. Pilots use it to judge the curve of the turn. They can see if the predicted path is turning too tight or too wide, especially with wind, and adjust their bank angle accordingly to make sure they roll out lined up.
Clever. So they're using that prediction to stay on track.
Yep. Then, as the aircraft gets further into the turn, say approaching 90 degrees of turn completed, they should be reestablishing really clear visual contact with the runway.
Okay, eyes back on the prize.
Right. And they start making finer adjustments to the bank angle based on what they see. At the same time, they're checking that vertical speed on the FMC descent page again. It should be steadily decreasing, maybe below 950 feet per minute by now.
And comparing that to?
Comparing it to the visual picture, especially the PPI lights on the ground, if they're available.
Right, the PPI Precision Approach Path Indicator, those lights beside the runway.
That's the one. Usually sets of lights, red and white. They tell you if you're too high, more white, too low, more red. Or right on the glide path, equal red and white. It's a primary visual cue for vertical guidance.
Okay, so visual PPI and instrument VS cross-check. Makes sense.
Now, as you get further around the turn, maybe about 135 degrees into it, so you've only got about 45 degrees left before you're lined up.
Almost there.
This is a critical moment. The pilot adjusts the bank angle very precisely so that the end of that trend vector, that 30-second predictor, looks like it's just tangential to the extended center line of the runway on the map display. Like, it's just kissing the line.
Why tangential?
Because if the predictor is tangential at that point, it guarantees that when you continue the turn and rollout, you'll be perfectly aligned with the runway center line. It's geometry in action.
Wow, that's neat.
It is. And Captain Chopra makes a really important point here. Pilots need to avoid the common trap of just staring at the runway threshold, the numbers at the start of the runway.
Why is that bad?
Because you can be pointed directly at the threshold, but still be significantly off the center line if you aren't looking further down the entire length of the runway to judge your alignment.
Ah, look down the runway, not just at the start. Got it.
Okay, now we get to the really clever part, where all these visual and instrument cues converge in the final stages. There's this key aha moment, another approach gate.
What happens?
It's when that path trend vector on the map display just touches the 2.5 nautical mile circle that crosses the runway center line.
Okay, predictor hits the 2.5 mile mark.
At that exact moment, the pilot checks their altitude. It should be decreasing through 1,000 feet AGL.
1,000 feet.
And simultaneously, that vertical speed on the FMC descent page should be reading somewhere between, say, 800 and 850 feet per minute.
That seems incredibly specific. 1,000 feet AGL, just as the 30-second predictor hits the 2.5 mile circle? Why that number?
It's actually brilliant maths. Remember, the trend vector shows where you'll be in 30 seconds.
Right.
If you're descending at, let's say, a steady 500 feet per minute during that turn,
okay,
then in 30 seconds, you'll be 250 feet lower than you are right now.
Half a minute's descent, right?
Now, on a standard 3-degree glide path, which is what most approaches aim for, when you are actually at 2.5 nautical miles from the threshold, Your target altitude is about 750 feet AGL.
Okay, 750 feet at 2.5 miles.
So add the 250 feet you'll descend in the next 30 seconds to the 750 feet target height at the 2.5 mile point.
250 plus 750 is 1,000 feet.
Exactly. So seeing 1,000 feet AGL just as the trend vector kisses the 2.5 mile circle tells the pilot they're perfectly on the correct vertical profile well before they actually reach 2.5 miles. It's an early confirmation.
That is clever. A predictive check. So at this point, things are really coming together.
Absolutely. The runway is clearly visible ahead. You're visually lining up with the center line, looking down its whole length. You're judging your height using the PAPI lights. And you've got these fantastic cross checks from the FMC and map display. The lateral path is confirmed by that tangential trend vector, and the vertical path is confirmed by hitting that 1,000-foot gate at the right moment. Visual and instrument agreeing.
It's like a symphony of information, but focused information.
Precisely. Now, with the flight path basically nailed, the pilot selects the final landing flap setting.
Flaps full down, usually.
Typically, yeah. Landing flaps selected. They anticipate the nose wanting to pitch down a bit more as the flaps extend and the plane slows, so they're ready with trim. They'll also need to add some thrust to maintain the correct final approach speed with the increased drag.
It sounds like things are happening very quickly here.
Oh, it's highly dynamic. Pilots really need to stay ahead of the aircraft, anticipating these changes, making smooth control inputs to avoid getting destabilized.
So stay ahead of the game.
Definitely. Then they roll out smoothly, perfectly aligned with the center line, call for the landing checklist completion, maintain a slight crab angle into the wind if there's a crosswind.
To counteract the drift.
And just double check that the track line on the map display is pointing right down the runway symbol. Final confirmation.
And there's a final critical altitude check, isn't there, for stability?
Yes, absolutely crucial. By 500 feet above the ground, the aircraft must be fully stabilized.
Meaning
it's at the correct landing speed, in the correct landing configuration, gear down, flat set, on the correct flight path, both laterally and vertically, and with a stable rate of descent. Everything's settled.
And if it's not stabilized by 500 feet?
Go around, no question. Abort the landing and try again. Safety first. But assuming it is stabilized from 500 feet down, the landing is flown exactly like any other normal approach.
So that visual circuit essentially gets you perfectly positioned and stabilized by 500 feet.
That's the goal. And the underlying principle for making the whole thing work, as Captain Chopra emphasizes, is focus. At any single point in that circuit, there's a specific task to do, and only a small, manageable set of key parameters to monitor.
Don't get overloaded.
Exactly. Yeah. Getting fixated on something minor, or scanning outside too much without cross-checking the instruments, or vice versa. That's how things can go wrong.
Yeah.
So, yes, they use aids, but fundamentally it's still flown visually. You need that continuous contact eyes on the runway, the terrain, other traffic.
Wow. What an incredible display of skill, really. We've kind of walked through this intricate dance of the visual circuit, from the mental prep needed beforehand to using those FMC cues precisely and constantly cross-checking with the real visual picture. All to land these massive machines with amazing precision, sometimes without the full suite of instrument guidance we normally imagine.
It's impressive stuff. And remember, this deep dive used the parameters from Captain Chopra, mostly for the B-737. But he really encourages pilots to develop similar, precise procedures for whatever aircraft they fly. Tailor it to the specific machine.
That makes sense.
So here's a thought to leave you with. Imagine a situation where maybe the map display isn't fully working. Perhaps an FMC failure limits its functionality.
Okay, less tech available.
How would a pilot adapt? Could they use just the minimal information left? Maybe just the TCS traffic display showing nearby planes as a circle? Or perhaps just basic distance arcs on the navigation display without the fancy trend vectors and fixed pages?
Could they still fly a safe visual circuit with even less help?
How would they use those bare-bones cues to maintain awareness and still execute a safe landing? What stands out to you the most about this blend of high-tech assistance and fundamental flying skill?
It really makes you think. Next time you're on a flight, maybe picture that pilot up front, building that incredible mental map, using every cue available to bring you down safely.